All right, let me not delay this any further. Martin Hara.
Okay, thank you very much. Yeah, so this is the last lecture of this session, which is dedicated to the works of this year's 4 Fields medalists. So my lecture is going to be on the work of Hugo Duménil-Copin. And so it's going to be in a quite different topic from the previous lectures. And I'm going to focus on one aspect of his work, which is really one of the main aspects. So it's a topic on which he has made amazing progress in the last decade. And that's the study of the critical Potts model. So I don't expect everybody in the audience to know what the Potts model is. I'm going to explain that in a minute. I don't expect you to know what it means for a model to be critical either. So I'm going to explain that as well. And so here I just wrote down a list of some of the topics that I want to touch upon in this lecture. And of course, we're not going to be able to go into much detail. But I want to, here and there, I want to give you sort of little nuggets of proof just to show you, the sort of techniques that show up, the sort of, statements that one can show in this area. Now, the Potts model, or the random cluster model, so here we're talking about kind of statistical mechanics models. And so by and large, these are sort of lattice models. So you imagine you have a piece of lattice, for example, ZD. And then you have some local state space. So at each vertex of your graph, say ZD, you have some kind of state space that's attached. And in many of these models, that state space is very simple. So for example, in the Potts model, it just consists of the integers from 1 to q. And so a state of the model, you can view it as a coloring of your graph, right? So you have a graph, and now each vertex, you give it a color, and there are q different colors, okay? And q is just a parameter of the model. It's fixed. So q could be like 3. So you just have coloring red, green, blue of each vertex of your graph. And now what you do in these statistical mechanics models is you build a probability measure on these configurations, and your probability measure typically favors certain configurations, right? So you typically have some kind of an energy functional, and you favor configurations that have low energy. And in the case of the Potts model, what you're trying to favor is neighboring vertices having the same color. Okay, so that's what you're favoring. And so the way you build your probability measure here is you just say, well, you look at all the edges of your graph, and then for every edge, either the 2 vertices that it connects have the same color or they don't. And so you just look at the number of edges that do connect vertices with the same color, okay? And then you say that, well, your configuration has probability that's proportional to the exponential of some parameter, which you call beta, times the number of these edges, right? So the most likely configuration is the one where all the vertices have the same color, right? Because that's, of course, the one where the number of edges connecting vertices of the same color is largest, because it's all of the edges. But then there's only very few such configurations, right? There's only q of them. And so even though that's the most likely configurations, they're actually still not very, they're actually less, there's only q of them, and there are many, many other types of configuration. And so it's actually quite unlikely that you see one of those, even though if you really just look at the likelihood of individual configuration, they are the most likely ones. It turns out there's actually a generalization of that model for non-integer values of q as well. So the way I've described it, obviously wouldn't make sense for non-integer values because Q just determines the number of colors, okay? But there's a slightly different model, which is called the random cluster model, which was introduced by Fortuyn and Castellin in the 60s. And that one is a model on, if you want, subgraphs of your original graph. So again, it's the same sort of situation. So you fix a graph. And now a configuration, instead of being a coloring of the vertices of the graph, it's a subgraph of your graph. So basically, you look at, for each edge of the graph, you decide to either include it or not, right? So that's now your space of possible configurations. And the way you construct a probability measure on this configuration, or if you want, the way you draw a random subgraph of your graph, is you say, well, the probability of seeing a certain subgraph is just given by this formula here. So a subgraph, I can basically describe it by a function from the vertices into 0, 1, right? So it's sort of 1, from the edges, sorry, into 0, 1. So it's 1 if the edge is included in your subgraph, and it's 0 if the edge is not included. So I can encode a subgraph by just a function omega from the edges into 0, 1. And then the probability of seeing a subgraph omega is proportional to p times the number, p to the power of the number of edges that are included times 1 minus p times the number of non-included edges. And then there's an extra factor, which is q, which is now the same q parameter, but now it doesn't have to be an integer, to the power of the number of connected components of your subgraph. So if you didn't have that extra factor, say if q is equal to 1, right, then that the p to the power open edges times 1 minus p to the power closed edges, that would simply be the probability measure that you get by, well, for each edge, you simply independently choose to either include it or not with probability p. Right? So then that would give you this factor here. But now what you do is you weigh this, you re-weigh this by the number of connected components. Okay? And it turns out that that random cluster model and the Potts model, they're extremely closely related to each other. And the way in which they're, right, so both of them have, so if Q is fixed, then both of these models depend on one parameter. In the case of the Potts model, it was that parameter beta, where the probability of seeing a configuration is e to the beta times the energy, if you want. Whereas in the random cluster model, it was that parameter p, which is essentially, in the absence of q, which would just be the probability of including each edge. And if you relate p and beta by this expression here, then the Potts model and the random cluster model are very closely related in the following sense. You can couple them. So what does it mean to couple two models? It's basically to build a probability measure on the product space so that if you project on one component, you get one model. If you project on the other component, you get the other model. Okay, so that's a coupling. So for example, you can always couple any two models by just taking the product measure. But in general, a coupling can be a much more complicated measure, which is not the product measure, but which still has the property that if you project on the first factor, you get the first measure. If you project on the second factor, you get the second one, right? And so here it turns out that it's possible to couple them in such a way that the edges that are included in the subgraph in the random cluster model basically correspond to the edges that connect two vertices with the same color in the Potts model, okay, in the following, and at least in one direction, right, in the sense that if an edge is included in the random cluster model, then on the Potts model side, that edge connects two vertices of the same color, but not necessarily in the other direction. And if you look at the conditional distributions, they have sort of nice uniformity properties. So if you condition on the Potts configuration, so in the sense that you have your measure on Potts model on one side, random cluster model on the other side, you fix what you see on the Potts model side, so you fix a coloring, if you want, on the graph, then what you see on the other side is simply you take your coloring of the graph, and then this coloring of the graph, it determines a subgraph by simply keeping those edges that connect to vertices of the same color, right? And now on the random graph model, it's not that subgraph that you keep, but it's the one that you get from those edges. Only for each of these edges, you sort of flip a coin, a biased coin with probability P, and you only keep the ones that come up heads, okay? And in the other direction, if you condition on the random graph model, so you have a random subgraph of your original graph, and then the configuration that you see on the Potts side, the coloring that you see is simply, well, you look at all the connected components of your random subgraph, and then each connected component, you just assign it a color, and you do that independently, right? And so that gives you a coloring on the other side. And the coupling that you can construct with this very specific relation between the parameter has these properties. So the point here is that in that sense, these two models are very, very similar because you can construct that coupling, which is such that even though the models individually are quite complicated, the coupling is so that if you know what happens on one side, then conditional on that, what happens on the other side is very simple, right? Because it's just a construction which like IID kind of variables, right? So in that sense, these two models are very closely related. And so in the rest of the lecture, all the results that I'm going to talk about can be proven, essentially the same result can be proven for either one of the two models. And typically you prove it for one of the two, very often for the random cluster model, and then you can transfer it to the other one using that coupling, okay? So now the other word, so now I've described, if you want, what the Potts model is, which was, so maybe just as an aside, right? I mean, this seems like a somewhat random kind of model, right? I mean, you can come up with loads of models of statistical mechanics. The Potts model it's one of the simplest models you can write down. So in the case where there's only two colors, which is, if you want, even the simplest case of the Potts model, the simplest interesting case of the Potts model, then this model is equivalent to the Ising model, which is one of the somehow oldest and most famous models of statistical mechanics, which is sort of a standard toy model for magnetism. And if you want, the reason why, even from a physicist's perspective, it's interesting to study these kinds of very simple models, right? I mean, there's obviously nobody would ever believe that these models sort of generally describe what actually happens at a microscopic level, even in a magnet or anything. The reason why even for physicists it's interesting to study these models is that there's a belief that when you look at these models at criticality or near criticality, and I'm going to explain in a second what that means, then they have certain universal features in the sense that if you take more complicated models that are maybe more realistic in terms of what actually happens in an actual ferromagnet, then at the critical temperature, they would actually behave in pretty much the same way as these mathematical toy models. And so even though these models are very, very simple, they still have actual predictive power at the physical level. Okay, so that's why they're interesting to study. And so now what does criticality mean here? So remember, in this model, there's one parameter, which is beta for the POTS model, or P for the random cluster model. And it turns out that these models change completely in behavior as that parameter crosses a threshold. And so I show you in a simulation. So here, we're looking at the POTS model on a chunk of Z2, right? So the Z2 is the screen. It's about 500 times 500. It's a chunk of Z2 that's about 500 times 500. And we've got 4 colors, okay? And here I've just colored every vertex just in a completely random way, right, independently. So I take this as my initial data, and I actually, what I'm going to do is I'm going to run like a dynamical version of the POTS model, okay? So I'm going to introduce time in the model. So right now there was no time, but I just introduced time in such a way that as time goes on, after a while, what you're going to see is basically it converges, if you want, to the POTS model. And I can adjust the parameters. So here, the parameter e to the 1 over t, so e to the beta is 4, and the number of colors is 4. And so if I run it, I see something like this. So here you see the 4 colors. So there's red, green, blue, and magenta. And what happens is that after a while, one of the colors just takes over, right? So here, it's blue that basically takes over. It doesn't completely take over, right? You see these little specks of other colors that appear. But essentially, one of them takes over. And if you want, that's not too surprising, right? Because we saw that in principle, the most likely configuration should be the one where all the colors are the same, right? And so it's not too surprising that essentially one color takes over, right? But it turns out if you change the value of that parameter, so here the parameter is exponential of beta is 4. So if I reset this and make it, say, 2, right? Then it just stays essentially random, right? So at 4, you saw one of the colors takes over. At 2, it essentially stays random. So I can take 3. Well, there it's not clear, right? So it turns out that in this particular case, 3 is actually the critical parameter, in the sense that if I make it a tiny bit more than 3, then it really behaves more like 4. So if I make it 3.1, right, then you already kind of see what's happening, right? So it's slower than when the value of the parameter is 4. But you kind of see that, well, you have these kind of large regions that form. Within each region, one color clearly dominates. And the domains between these regions, they sort of move in such a way that, essentially, if we waited for a while, one of the regions would end up just dominating, right? Whereas if I take something like 2.9, then it immediately looks like this, essentially looks random, except that what you see is that, so let me just freeze the simulation for a second. Right, so what you see is it doesn't quite look as though I colored each guy independently with a color. You see that you have these sort of chunks of color that now have a size which is sort of bigger than just 1 pixel. Right, so essentially, each cluster now has typically a size of maybe, a dozen or so vertices across, instead of just being typically of the size of 1 or 2 vertices, which is what you would get if you simply color it as random. But the point here is that there's a very clear and very abrupt change in behavior at one very specific value of beta. And in this particular case, it turns out to be the one so that e to the beta is equal to 3. Sorry?
Can you go back to 3?
I can go back to 3. Right, so now, so at 3, so what happens at 3, right? So at 3, what you see is that it's kind of in between the two. So it's not really, you don't have any of the colors dominating, but you don't either have clusters of a sort of fixed size. That's right. So the largest clusters have about the size of the whole picture, right? Which is, in some sense, not quite true. So it turns out to be the case here. In reality, if we made it infinitely big, then you wouldn't actually have infinite clusters. So the clusters would still have finite size, but the size is heavy-tailed. So somehow you have a quite high probability of seeing very, very large clusters. Okay. Right. So now there's a very basic question you can ask now, which is, what's the actual value, the critical value that discriminates between these two behaviors? And here we've seen, in the case of 4 colors, the value 3 seems to discriminate between the two. And this you can actually predict because the Potts model, or this random cluster model, it exhibits a certain duality, and the Z2 lattice is self-dual. Okay? I'm going to explain in a second what that means. And the model on the dual, so there's a correspondence between the Potts model on any graph, any planar graph, and the Potts model on the dual graph, but with different parameters. And so then a natural conjecture would be to say, well, there's one special value of the parameter, which is the one for which the model is self-dual, right? And so you would expect that would be the critical value, right? So it turns out the way it's related is that e to the beta minus 1, e to the beta star minus 1 times e to the beta minus 1 is q, where beta star is the value of beta for the model on the dual graph, right? And if you sort of solve for that, right, so if you ask yourself, what's the beta so that beta star is equal to beta, you find this, right? You find this 1 plus square root of q, and well, in the particular case where q is equal to 4, that's indeed 3, right? So that was the 1 plus square root of 4 that we've seen in the simulation. So that's an obvious conjecture, and it had been conjectured, pretty much ever since the model of that duality was discovered, which was, I guess, pretty much at the beginning, somehow in the late 60s or early 70s. But surprisingly, it actually took until the work of Beffara and Duminier-Copin about 10 years ago to actually prove that conjecture. So let me, right, so it was known, yes, so it was known in some special cases before, right? So in the case, Q equal 2 was, of course, much better studied. So that was the Ising model, as I already mentioned. And so that was studied already before even the random cluster model was even invented. And Onsager famously computed the value of the critical temperature and, of course, completely solved the Ising model in 2 dimensions back in the 40s. Then Q equal 1, which somehow seems somewhat less interesting, but from that point of view, it is actually, even the case Q equal 1 is actually interesting. And that was, again, in that particular case, you get that the critical point, so the Q equal 1 only makes sense in the random cluster side, not so much on the pod side. And so on the random cluster side, this simply corresponds to opening each edge independently with probability P, and then it was proven by Kasten back in the 80s that the critical probability is indeed a half, which corresponds to the self-dual one on the square lattice. And again, that was conjectured much, much earlier, but it took until Kasten to actually prove it. And then for large values of Q, somehow Q bigger than 26 or something like this, there was a proof in the 80s. But for arbitrary values of Q, the conjecture was actually only proven by Beffarah and Duminil-Copin in 2012. So I don't want to go too much into the proof of that conjecture, but I want to explain how that duality works, so why there is that duality, right? Because that's actually quite simple to see. So first, so here I've drawn a configuration for the random cluster model, right? So my graph is again the square lattice, and so here I've drawn a subgraph of the square lattice where simply some of the edges are included, that's the black ones, and some are not, which still show up in light gray. And given such a configuration, there's a dual configuration. So the dual lattice, a dual graph to a planar graph, is the graph where the vertices for the dual graph are the faces of the original graph, okay? And two vertices are connected in the dual graph if the corresponding faces share an edge in the original graph, okay? So this notion, of course, only makes sense for planar graphs. And so in the case of the square lattice, of course, the dual graph is again a square lattice, right? Because the faces are just the actual squares, and then if you connect faces that are adjacent, then you get another square lattice. Okay, so the square lattice is self-dual. And now you see that if you take any edge in the dual graph, right, so that would be an edge that essentially connects the centers of two adjacent squares, so two adjacent faces in the original graph, then you get there's a natural subgraph of the dual graph that corresponds to the subgraph of the original graph by keeping all the edges in the dual graph so that, so if you take an edge of the dual graph, so you have two adjacent squares, the edge that connects the centers of these squares is going to cross an edge of the original graph, right, which is the edge of the original graph that separates the two squares. And now what you do is, well, for those edges in the original graph that are part of your configuration, you do not take the corresponding edge in the dual configuration, whereas for those that are not part of your configuration, you do include the ones in the dual configuration. So that's what I've drawn in the picture here, right? So the configuration that we've chosen are the black edges. So the black lines are a subset of the edges of the original graph. And then these blue lines are a subset of the edges of the dual graph. And it's precisely those edges that do not cross a black edge, okay? So you see that the blue edges are the edges in the dual graph that don't cross any black edge. Okay, so in that way, you have a map that maps configurations from the original graph into configurations for the dual graph, right? And now the claim is that if you draw the original configuration according to the probability measure given by the random cluster model for a certain parameter p, and then you look at the corresponding configuration according to that procedure on the dual graph, then that one has the law also of a random cluster model, but for a different value of P. Okay? And in order to see that, there's essentially one thing one needs to remark is that connected components in the original configuration correspond to faces of the dual configuration, right? And so that's what I try to illustrate on this picture. So again, on the left, I have that particular configuration that we already had on the previous slide. So it's just an arbitrary subgraph of that piece of two-dimensional lattice. And in red here, I've drawn one of the connected components. And now if you look at the dual configuration, which are all these blue lines on the right, well, you see that here in pink, I've colored a face of the dual configuration, and that face of the dual configuration consists simply of all the squares that are touched by that connecting component in the original configuration, right? And you see on the picture that if you take any connected component here, that determines a face of the dual configuration. And that includes, so here connected components also include isolated vertices. Okay, so they are not drawn, but for example here, you have an isolated vertex, and that isolated vertex corresponds to this face here, right? This small face, and so on. So there's a one-to-one correspondence between connected components of a random cluster configuration and faces of the dual configuration. And another relation between the two, which is obvious from the definition, is that if I take the number of edges of my configuration and I add the number of edges of the dual configuration, then that's equal to the total number of edges, because that's basically how it was defined, right? Because for each edge, for each edge of my original graph, I have an edge in the dual graph that crosses it, and the dual configuration is precisely defined by keeping exactly those that aren't taken in the original configuration. And so if I add the two, I get all the edges back. And so then once we have noted these two facts, then we know that there's also a variant of the Euler formula here, which is that if I take any subgraph of that piece of two-dimensional lattice, and I look at the number of vertices, which is now the total number of vertices of the lattice, of that piece of lattice, plus the number of faces, that's equal to 1, plus the number of edges, plus the number of connected components. Right, so this is basically just a version of Euler's formula. And then there's the two relations that we just discussed. And so once we have, whoops, what's happening here? So once we have these, oh, what happened? Now my slides are gone. Okay. Sorry about that. Right, so now remember that by definition of the random cluster model, the probability of seeing a configuration was given by this expression, was p over 1 minus p to the power of the number of open edges, the number of edges in our subgraph, times q to the number of connected components. And now this is proportional. So if we now relate this to the dual configuration, we see that, well, the number of edges in our random cluster configuration is equal to the total number of edges, which is fixed, which doesn't depend on which subgraph I'm looking at, right? That's just the number of edges in my fixed chunk of Z2, minus the number of edges in the dual configuration. So I can just replace here this E, the number of edges in my configuration, by minus the number of edges in the dual configuration. And because of that relation between connected components of the original configuration and faces of the dual configuration, I can replace this here by the number of faces in the dual configuration, right? And then I can apply Euler's formula here, and I can replace the number of faces by the number of edges plus the number of connected components. And this 1 and this total number of vertices, I can forget about it, because again, that's something that doesn't depend on the specific configuration I'm looking at. And so it's always the same, and so it can be absorbed in the proportionality factor. Right? And then I simply move that factor around, and I include it in this prefactor here. And then I can simply choose the value P star, which is such that P star over 1 minus P star is equal to that quantity here. And then the expression that I've got here is exactly the same as the expression I started with, but now for the dual configuration, right? And so that tells you that the model for the dual configuration is exactly the same as the one for the original one, except that P had to be replaced by P star, and the relation between P and P star is the one that's given by sort of the last equality on that slide, right? So that's how that duality here works. Now, so that was about the actual value of the critical point. So then you can ask yourself, various questions about what happens at the critical point. And in particular, one question you can ask yourself, which is maybe sort of the simplest question that you can ask, is whether these models sort of extend to the infinite lattice in a unique way or not, right? And what you expect, you see again from these simulations, you expect that if you're at low temperature, below the critical temperature, so that's in this kind of regime, so there you expect to have one extension to the infinite lattice per color. Right? In some sense, that's the red extension that you see here. That would correspond to a measure on the infinite lattice, which is mostly red, and then with little bits of other color thrown in. And obviously, just by symmetry, none of the colors is different from any other. If there's one that's mainly red, there's also one that's mainly blue, and so on. Right? So here you would expect that there are 4 different measures on the infinite lattice that actually correspond, that you obtain as limits, possible limits of the measures on the finite lattice. And that's true. Whereas if you are at high temperature, you said something like this, and there none of the colors sort of dominates, and you don't really expect to have any kind of finite size influence anymore, right? Because clusters are very small, they don't really feel what's happening far away. And so in this regime, you expect that there's only one way of extending the measure to the infinite lattice. And so then the question is, what happens at the critical value, right? So at the critical value, do you have just one way of extending it to the infinite lattice, or do you have several ways of extending it to the infinite lattice? And surprisingly, the conjecture that was already given by Baxter in the 70s is that it depends on the number of colors. So the conjecture was that if the number of colors is 4 or less, then at the critical temperature, there's still exactly one way of extending it to the infinite lattice. Whereas if the colors is more than 4, then there's actually the number of ways of extending it is equal to the number of colors plus 1. Okay? And again, that was open for a long time, and it was proven, well, there were 2 completely separate papers. The proofs have essentially nothing to do with each other. And there's, well, one proof that proves, one half of the conjecture and one paper that proves of the other half of the conjecture. So again, here I don't want to go into the details of the proofs, but I want to actually show you what does this actually say about the, how can you tell the difference between the situation that you've got with 4 colors or less and the situation with 5 colors or more. And so one way of seeing the situation, seeing the difference, is if you now put boundary conditions. So what I did so far in the simulation, I actually put this thing on a torus. So I put like periodic boundary conditions. So I can do boundary conditions where I sort of fix the color on the boundary. So I fix it, say, red on half of the boundary and green on the other half. Okay? And now, if at the critical temperature, there's a unique way of extending the measure to the infinite lattice, then you'd expect that what you see sort of in the bulk of the picture shouldn't really depend on what you do on the boundary. Right? Whereas if there's a non-unique way of extending it, then it should depend on it. So now if we take the 4-color case, actually, I should reset that. So here now, I've got the case of 4 colors. The boundary is such that at the top and on the left of the screen, it's red, and at the bottom and on the right, it's green, right? And you sort of see that, but in the center, you see, in some sense, if we wait for a while here, the green really sort of invades quite a bit into the red and vice versa, and you have really quite large chunks of other colors that appear in the middle. Now, on the other hand, so if I take the case of, the next square of an integer, which is 9, and then the critical value is 4, then what you see here is really quite different. So let me actually reset that with this sort of triangular initial condition. So here what you see is really quite different. What you see is that there's a green region that remains sort of relatively well defined, right? So there's a green region that has sort of little islands of other colors. There's a red region that has islands of other colors. And in between, you see this sort of disordered region, right, where you have all 9 colors sort of appearing that are kind of mixed together, and that forms some sort of a boundary layer between the green region and the red region. And that really corresponds to the different extensions to the infinite lattice, right? So here there are the extensions that correspond to essentially one color dominating and the other colors sort of just creating small islands. And then there is the +1, which is the phase that you see sort of in the middle, which can also be extended to the whole lattice. And that's a disordered phase where in some sense none of the colors dominates. And they actually have in some sense clusters of roughly well-defined size. Okay. So you have really quite a, it's really somehow quite remarkable here that there's this difference in behavior between the situation where you have 4 colors, and the case where you have more than, less than 4 colors or more than 4 colors. So there's now another result I just want to say a few words about is about, we've seen the fact that if we put ourselves at high temperature, so in the sense, so that was this disordered phase, where we essentially see clusters of somehow well-defined size, then, well, we've seen exactly that, right? We've seen that the size of the cluster seems somewhat well-defined. And so that suggests that if we look at correlations, so for example, you ask yourself, if you take 2 lattice points that are at a certain distance x apart, and you look at the color at this lattice point and the color at that lattice point, and then you ask yourself what's the correlation between the value of the color here and the value of the color there, then since the size of the clusters is well defined, you expect that correlation to decay rapidly. Right? And of course, in this type of business, decaying rapidly typically means decaying exponentially. And so the conjecture was that, well, as soon as the temperature is above the critical temperature, you have this exponential decay of correlations, which is now the reason why, and this is a theorem from a few years ago by Hugo Dumil, Capin, Raoufi, and Tassion. And the theorem is not just true for the square lattice, it's actually true in any dimension. So for example, the fact that the lattice is self-dual is very much, well, being self-dual is only defined in 2 dimensions, right? So it's really very much a property of dimension 2. But the fact that you have this phase transition, that you have this change in behavior that's quite abrupt at one specific value of the parameter, that's true in every dimension, except in dimension 1. But in the other dimensions, there is no closed form expression that is known for the critical value of the parameter. Right? So the value of the critical parameter is only known in dimension 2. And so that makes it, if you want, somewhat remarkable that you're able to prove these kind of theorems because you don't actually know the value of this critical dimension. Right? And so the way that proof goes, so there I just wanted to say a few words about the proof because it's really quite beautiful. And it's interesting because it relates to tools that were developed in a completely different context, actually in theoretical computer science. And so here the proof relies on a generalization of a tool that's called the OSSS inequality. So let me just say a few words about that. So the context here, it's the context of sort of the behavior sensitivity analysis of Boolean functions. So you've got a finite set, and to each element of the set, you assign a Boolean variable, right? So you can have the value 0 or 1. And then you take a function that goes from that state space. So the state space is simply 0, 1 to the power of your finite set. And you take a function that goes from that into, well, typically the function is Boolean as well. So here I wrote it as taking values in the interval 0, 1. Actually, in many cases of interest, the value itself only takes the values, the function itself only takes the values 0 and 1. And now what you do is you try to, if you want, guess the value of your function by looking at as little as possible of the input, right? So you know what the function is, but you don't know what input it was given. Okay, so you have a probability measure on the space of all possible inputs, and now you want to reveal properties about the input without looking at the whole input, and you want to reveal as little as possible. You ask yourself sort of like, how much do I have to reveal in order to be able to determine the value of f? Okay? And so now you take any function f of that type, and you take any algorithm that reveals values of the input one by one, right? So the input is basically a Boolean sequence. So you have this finite set E, and then at each point of E, you have a Boolean variable that's attached. And you imagine that you don't know these Boolean values, and you just discover them one by one, but you're allowed to choose an algorithm in such a way that you decide which one to uncover next, depending on the values that you've seen before, right? So you sort of uncover values one by one, but you decide to look at, you can choose where to look next, depending on what you've seen before, okay? And then you stop once you've seen enough to be sure that, you know that with that, you've determined the value of f. Okay, so like revealing anything further wouldn't actually gain any further information on the value of f. And then if the probability measure on these Boolean variables has a certain monotonicity property, so in the original theorem, in the original OSSS paper, the probability measure was assumed to be simply IID. So they were just simply assumed to be independent Boolean random variables. And the generalization in that paper by Hugo, Raoufi, and Tassion was to actually generalize this to all probability measures that have certain monotonicity property, and it turns out that the random cluster measure has precisely that monotonicity property. And so you can take as your space sort of the edges of your graph, and as your probability measure, a random cluster measure. And then you have this inequality which essentially bounds the variance of the function f by this sum over the probability that a given edge or a given element of your set was uncovered times the influence of that edge or that variable of your set on the function f, right? So this quantity here is the influence of one specific variable on the value of f. So it's the covariance between f and what you get by flipping that specific Boolean variable. And so in the case of this sharpness of phase transition, you want to apply this to the random cluster model with f being, so you take the random cluster model on a big ball, and f is the function which is 1 if the origin is connected to the boundary of the ball via your subgraph, via the random subgraph that you've drawn from the configuration, right? So that's a Boolean function. Okay, so it's either 1 if you're connected or it's 0 if you're not connected. And it takes as an input the random subgraph of your chunk of Z2 or ZD, or actually it works for any transient graph. And it has the right monotonicity property to apply that theorem. And then what they do is they derive a certain differential inequality for the expectation of that function. So basically the probability that the origin is connected to the boundary of that ball in your subgraph. And this differential inequality is derived using that generalization of this OSSS formula. Okay, so you get a certain differential inequality, and, well, basically you get a sequence of differential inequality, one for every value of n, where n is somehow the size of your ball. And then what you can prove is that this sequence of differential inequalities satisfies a certain dichotomy. And then basically it tells you that this probability, the probability of the origin being connected to the boundary at the end of the day has to either be really, really small, so it has to either be exponentially small, or it has to be actually pretty large. And there is exactly one value of beta in which there's a transition between the two behaviors. But then this comes out as a completely general fact for sort of any sequence of functions that satisfies that sequence of differential inequalities. Okay, so I think I'm sort of getting towards the end of my time. So I just wanted, the last point I wanted to mention was, so that's another beautiful result, which is related to the fact that for all of these statistical mechanics models, what one expects is that if you are at the critical value and you look at the behavior at very large scales, you see a certain conformal invariance for these models. And I mean, that's not at all obvious, right? Because, I mean, they are defined on a lattice. And so in principle, you could imagine that the lattice structure somehow has some, there's some survival of the lattice structure in the behavior at large scale of these models. But it turns out that at the critical value of the parameter, typically, the lattice structure sort of gets washed out. And what you see at large scales is, well, not only scale invariant, but also, well, sort of scale invariant and rotation invariant. And therefore, you would expect also conformal invariant. And that in many cases, so this is expected, but it's actually not known in that many cases. So it's known for the Ising model, at least in certain instances of the Ising model, and that was one of the big results that Smirnov managed to prove about 20 years ago. And for the Potts model, this is actually still not known for the general Potts model. And so one of the recent results is to at least show that you actually have rotation invariance at large scale, so that the structure of the lattice get washed away at the critical point. If you look at large scale sort of connectivity properties, if you want, of the random cluster that you draw from your random cluster model. And so that, of course, is one of the main ingredients. I mean, you would expect that once you have this, it shouldn't be such a huge step to actually get conformal invariance, which is what you really want, because conformal invariance then gives you all sorts of nice properties for the scaling limit of these models. But that's still a major open question. And so I think I stop here, and thank you very much for your attention.
Thank you very much for the talk. We have time for a couple of questions, if you like. And I also want to remind the audience that there is a write-up of each of these talks online in the AMS website. You can search for Current Events Bulletin and AMS, and you'll find it right away. Are there any questions that want to be asked? Otherwise, we can have them informally afterwards. No, I think everybody is a little worn out. Ah, here's a question, yes. Go ahead.
Or is this not on? Oh, it's on. Okay, I can hear me. Can you comment on this disordered phase for Q greater than 4? So the disordered low temperature phase. Or not disordered, but
Right. Well, so what happens is that you basically get, so you can take limits either, so you could take the, say you fix the boundary condition at a certain color, and then you take the infinite volume limit, and then you would get one of the Q ordered phases somehow. And the way you would see the disordered phase would be to put yourself at a temperature that's slightly higher than the critical temperature. So then you have uniqueness of the phase, and it would be disordered. And then you take that measure, and you send the temperature to the critical one, right? And then you would have a limit as well, and that would be that one. And so in the case where Q is bigger than 4, these limits don't match, right? And so you get these Q plus 1 different limits. Whereas in the case Q less than 4, if you do any of these procedures, the limits actually always match up, and you just get one possible limit.
Can you say anything about correlation length in that situation? Like, I don't know if there's conjectures by
Yeah, so I don't know. I think, I don't know actually. Yeah, so I'm not sufficient expert in that. So I don't know if I don't know if there's exponential decay of correlations, for example, at the, I would probably think not, but I don't know.
And it's the reason for there not, so the conjecture on the previous slide, I think, said conformal invariance for Q less than 4, or Q less than or equal to 4, right?
Yes, so that's for Q less or equal to 4, because that actually, it exploits, it exploits the uniqueness of the infinite volume limit, yeah.
Cool, thanks.
Yeah.
All right. Unless there's another question? Oh, there's one over there. Greg, Laura.
Yeah, I just, the Baxter conjecture and now theorem, how did Baxter guess it? Or what's the intuition? Is that part of the proof? Or not the part of the proof, but is the proof use the intuition from the conjecture?
So I don't know how Baxter proved it, came up with the conjecture, but there is a link. So one way of seeing it, so at least the one that I know and which they use in one of the proofs, is that there is a link between the random cluster model and the 6 vertex model, but then that link actually breaks down on one side. I mean, when you look at that link, there is actually a clear difference between Q bigger than 4 and Q less than 4. The link only works for one of the two sides. I don't remember which one. But, yeah.
So you said you get sort of interesting things by starting with the temperature a little bit, I guess lower the temperature lower, so the number higher, and then decreasing it to the critical temperature. And I guess you can also, now that with the subgraph model, you can have Q varying uniformly, so you can sort of tie the temperature to the critical value for that Q, and then take a Q that's like slightly bigger than 4 and slowly lower it to 4.
I guess you could.
And so you're seeing sort of like a higher order phase transition, right? Because you have the phase transition in Q, keeping the fact that you have a phase transition in the temperature. So have you kind of like played around with that?
I have, well,
I mean, it'd be interesting.
I personally haven't published anything on the POTS model, right?
I guess
so this is all Hugo's work.
I mean, in terms of simulations. In terms of simulations. Oh, in terms of simulations, no, I haven't. So like you do the subgraph model with a fixed value of Q, you take the critical temperature, and now you lower the Q down to 4, and sort of see what happens, like with fixed, with different boundary conditions. It'd be interesting to see. Yeah.
So the problem with these things is that they kind of slow down a lot, right? So sort of like the closer you are to the critical temperature, the longer it takes for these things to equilibrate. So
And as I'm saying, you like run it at the critical temperature, where the critical temperature is moving with Q as you bring it down to 4. It'd be interesting to see what that would look like. Anyway, something to try out.
Yeah. Of course, these simulations only work for integer values of Q, right? I mean, because here I'm doing the coloring.
Yeah, that's why you would have to do it with like the subgraph
model.
Sure.
Okay, thank you again. I think it's time to wrap up the session for the year. Yes, thanks to all the speakers for a very interesting and entertaining afternoon.